Okay, so this is part 2 of Newton's first law of motion. And we're going to do a little bit of calculation on weight, so please pull out a calculator and hit pause. So the question is, what is your weight in newtons? So first of all, what do you need to do? Remember that the weight is equal to the mass times the acceleration due to gravity. Now remember that weight is a force. It's a special kind of force, so we call that force, special kind of force, we call that a weight. And as all forces are concerned, you're going to take the weight, or the force is equal to, in this case the weight, is equal to the mass times acceleration due to gravity. So first you will have to convert your weight in pounds into kilograms. Coincidentally, 2.2 pounds is equal to 1 kilogram. So you use the above equation, mass times acceleration due to gravity will give you your weight. So you go ahead and do that. Step 2 is done, equals, and you'll get your weight. So remember, weight is a measure of gravitational force. So it is a force. Okay? Weight is a force. Remember that. And so, because weight is a force is also equal to mass times acceleration due to gravity. Or, in this case, force is acceleration. Okay? Alright, so, what is your weight in newtons? Go ahead and calculate that. And if in case you don't know, you take your weight in pounds, okay? And if you weigh 100 pounds, you take 100 pounds divided by 2.2 pounds will give you your weight in kilograms. Then you take that, your mass in kilograms rather. Take that mass, multiply that by acceleration due to gravity, 9.80 meters per second squared, and you'll get your weight. It is not completely necessary to include the negative sign. You should, since weight is downwards. So we'll talk more about that in a little bit, but whether you use the negative sign or not, at this point in time, it doesn't really matter. Okay. So now, what is net force? Now, the word net is kind of difficult to understand if you don't know anything about accounting. Okay. Now, the term net force is the combination of all forces acting on an object. We call that the net force. So let's talk a little bit more, I guess, something you might be more familiar with. So if we'll talk about net income. Your net income is after all the money you have made with all the deductions from taxes and whatever, at the end of the day, your paycheck is what you get home, what you deposit into the bank. That is actually net income. So for example, your monthly income is $1,000. Okay, but that's your $1,000. That's before taxes. So after taxes goes away, let's just say they take away 20% of your money for taxes, you're left with $800. That is your net income. $800 your net income. So now what net forces is you have some forces in the positive direction, you got some forces in the negative direction, so on and so forth. After all those forces are balancing itself out, whatever is left is called a net force. Okay? That's basically what net force is. Now remember that forces are vector quantities, and because it is a vector quantity, it will include both a magnitude and a direction. So now here I have an example of a net force. So if force 1 is pushing in a negative direction at 20 newtons, force 2 is providing a force in a positive direction with 18 newtons. After the two forces balance each other out, you'll end up with 2 newtons for your net force. Now 2 newtons of net force has to go in some direction because forces are vector quantities. It will include both a magnitude and a direction. So it's 2 newtons in a negative direction, and that is basically what a net force is. After all the forces are balanced each other out, whatever's left is your net force. So now, what about equilibrium? What does equilibrium mean to you? Now, if equilibrium means to you where everything's at balance with each other, just like the old Eastern Oriental kind of a idea that equilibrium is like harmony, where there is a balance of light and dark, there is a balance of good and evil. In the case of forces, equilibrium means the balance of all forces. when you have a complete balance of all forces, what is the value of the net force then? Think about it. If you have a balance of all forces, which means that all of the forces, they balance each other out. There is no leftover forces. What is it then? So, the net force changes a state of motion for an object. So if you have a net force, that means there's an imbalance of force. If there is a net force, there's an imbalance of force. When there is equilibrium, there is a balance of all forces, which means the net force will now equal to 0. And if there is a net force of 0, when there's equilibrium, either the state of motion of that object will remain constant. What that means is if the net force is equal to 0, then that object's motion will either stay at rest, and it will continue to stay at rest because there's no net forces acting on it, or if the object's already moving, the net force being equal to 0, that object's motion won't go any faster, it won't change directions, it'll remain at a constant velocity. So this is kind of an important concept. So that means it's at rest or at a constant velocity in a straight line, no change in direction. So here I'm particularly proud of the fact that I did not do that, but somebody did. Then there is a balance of forces here, which is why the rocks can balance on top of each other. Okay, there is a downward force of gravity, and this little rock is providing a full upward force on this top rock, and there are no forces to the left or to the right of it, and so therefore this rock is now at balance, equilibrium. So this rock, these three rocks will remain at a state of rest until somebody applies a net force to it. Now this one is pretty cool, you know. It looks nice. So again, on equilibrium. Now you can look at the rocks resting on this tabletop. Since the rocks are not moving, we can say that these rocks have a net force of 0. So we can, if the rocks were moving at a constant velocity, we can also say that the net force is equal to 0. Now, what are the forces that are acting on this rock? Or let's look at this rock right there, this rock right here. What are the forces acting on this rock? If you said gravity, awesome. Gravity is definitely one of them. But gravity is pulling all objects downwards. In order for this rock to have a net force of 0, there must be some other force that is going to counteract the force of gravity. And we call that the normal force. Okay? A normal force is a force that will act at right angles to the surface. If the surface is perfectly horizontal, the normal force will work in the opposite direction as that horizontal surface. The word normal means at right angles to, perpendicular to. So what will happen if you have a surface that is diagonal? Say, for example, you know, like this. This is your line right there. That's your surface. Let's pretend that's your surface, like right here. Okay? And so normal force will be at right angles to that surface. It won't be perfectly vertical. It'll be kind of off at a diagonal line. Okay? At right angles to that surface. So how about this surface right over here? So it'd be at right angles at that surface. The normal force will be right angles to that surface, right like this. So that's equilibrium. If net force is equal to 0, all objects are going to have all its forces balance each other out. So now, vector addition of forces. Oh geez, more vector addition. Now, it would be very similar to what you had done before, where you would treat the same forces in the same way you would treat the vector analysis problems in the previous chapter. Okay? Except now we have an equation to those motion. We have an equation called F net is equal to ma. F net being 0 and ma being mass times acceleration. So we'll draw a free body diagram. What a free body diagram is, a diagram that will show us all the forces acting on the object. So this is an example of a free body diagram where we're looking at, well, a dog, and you had a chain being pulled this way. That chain being pulled in this diagonal in quadrant 1 is essentially the same as a chain being pulled upwards and another chain being pulled in a positive x direction. And so then the combination of these two forces will yield this resultant. So for all forces that are being treated on or applied onto an object, we can still break it up into the x direction and the y direction, just like before. Nothing's changed. The process is the same. Only difference is instead of a velocity, we have a force. Instead of a displacement, we now have a force. So what is a free body diagram? So it's basically a picture of an object with all the forces acting on the objects drawn to it using arrows. Arrows, again, is an indication of a vector because the length will basically be the magnitude, and the arrow direction is the direction of that vector. So a free body diagram is a way to put all the forces onto the object, and you will be able to see what's going on. So if I have this purple box sitting on a tabletop, there's a downward force of gravity and upward force of normal force. So downward force mg, m mass, g acceleration due to gravity, that's the weight. And a normal force is the force that's being applied upwards from that object. And that upward force is always perpendicular to the surface. So if the surface is horizontal, the normal force would be perpendicular, which is vertical. So this is an example of an object at rest and a free body diagram for the object at rest. So how do we do a vector addition problem? So if you have an object of 10 newtons and suspended on a rope, what force must be used to keep this object in a state of equilibrium? The ones in the PowerPoint and at the screencast will be kind of easy. When we get into the class, when we do practice problems next week, it'll become a little bit more difficult. Okay. Now, in order for us to determine the weight of the object, we also have to note that because this is suspended on a rope, it's not moving up or down, side to side, it's suspended, and therefore we can assume that the object is not moving. And because the object is not moving or accelerating in any way, we are saying that the net force is equal to 0. Now remember that if the object is moving, it has to be moving at a constant speed for the net force to be 0. So I have the diagram here. The weight of this object, because if the object of 10 newtons, this basically says this is how heavy it is. It has a weight of 10 newtons. Okay. So the object is 10 newtons. We're basically saying that the object is going to be suspended on a rope, not moving, and therefore it's going to be net force is 0. And in order for this object to have a equilibrium, we are saying that the upward force must also be 10 newtons. So then the following diagram for number 3 is saying, now how heavy is this object? Okay. Now, if we got two ropes here and here suspending this round object, has a certain weight. Now, remember, if the net force is equal to 0 for this example, the downward force must be equal to the total upward force. So we'll actually be doing this in class. So somebody in class should bring this up so we can work on it in class, and this will give you an idea how to do this. Okay, and let's ask some conceptual questions. And we'll be answering this in class. If the weight of the object in the previous problem didn't change, and if the angle between F1 and F2 was changed 140 degrees, what will happen to the value of F1 and F2? So we'll go ahead and answer that question in a few moments, and in class after we finish number 3, so you can have a better idea. And we'll work all these questions out. And again, number 5 is the same thing, and we'll talk a lot about these concept stuff, using a little bit of math to explain the concepts. So 3, 4, and 5 we'll be answering in class. Somebody remind me in class. Okay. Now this tightrope walker dude. Okay. The question is, why can't the tightrope ever be completely horizontal when a tightrope walker is standing on it? And so based upon what we have done in 3, 4, 5, 6, you'll be able to answer this question a little bit more concisely. Okay. So I will actually stop it here, and then at some point later on and during class we'll actually go and answer these questions, and this concludes part 2.